optical activity. So what we end up doing is taking a light, a source of energy, our sodium lamp, we pass it through a monochromator so we get a very single and particular wavelength of light. We polarize that light by passing it through a filter. We end up with one direction of light, or the axis of light is now moving only on one axis. When this then encounters our sample, if we have a chiral molecule, that light starts to bend, okay, or rotate off axis. The more chiral molecules it encounters, the more the light bends. Right? So we can end up then visualizing that bending result at the end and notice how far off axis we rotated. We can then correlate that back to the optical activity of the sample, meaning it's chiral. Okay? And we'd also have to take into consideration the concentration of our sample. Because remember, the more molecules you hit, the more it rotates. Yes?
I was going to ask a question related to that. Does the length of the sample matter?
Does the length of the sample matter? Okay. What happens if it's a shorter tube? Less time to interact with the particles, which means less rotation. So it's very similar to the idea of your Beer-Lambert law. Okay. Path length is important. That also has to factor into our calculations.
So you could technically have one sample long enough to cancel out its own effect?
What do you mean by cancel out?
Not technically cancel out, but it makes, yeah.
So if we have enough sample in there, the light will continue to rotate and rotate and rotate. What happens if we exceed 90 degrees? What would we end up recording that as? A rotation the other direction. So it appears to be something else. So whenever we build our samples, we need to be cognizant of that, and we try to aim for concentrations that are low enough that we don't see a full rotation on it. If you are suspicious that something like that is happening, what would you do?
Reduce it.
What do you mean reduce it?
You can reduce the path length so you can have...
Let's say your equipment's fixed. You can't change the path length. Change the concentration of your sample. See how the light rotates. If you reduce the concentration of the sample, so let's say you went in, let me kind of weird drawing it. Now let's say you noted something that came out over here. Okay. If you were to measure that, you'd end up saying that we went, I don't know why it marked it that way, in the positive direction as opposed to the negative direction, right? Because when we spin our little dials, we'll stop at that negative or 90 degree and we'll spin it back the other direction. Close enough? Okay. What happens if we change the concentration? If it was indeed positive, where should our reading be? It should be higher up here because there's, did I say decreasing the concentration? I said change. If we decrease the concentration, what should happen to our reading? Well, if it was indeed positive, it should become less positive. What if you end up noticing it becoming more positive? And then it was rotating the other direction. It just rotated in excess beyond that 90. Does that make sense? Okay. You're looking at kind of a issue experimentally. Doesn't really show up in any kind of exams. But thanks for asking it, because now I can. No, just kidding. Okay. So the next thing that we can go through and do is name these. We can go through and refer to our compounds as positive or minus. When we look at this, we're looking at a compound. What if our compound or our molecule has many chiral atoms within it? Does this tell us the arrangement of each of those chiral atoms? No, it only refers to the molecule. This means when we're trying to assign chirality to an atom, that RS nomenclature system, okay, which was in the video that theoretically you had a chance to watch, doesn't match to this. Because optical activity applies to the molecule. RNS applies to an atom. Okay? And technically every atom that is chiral. Okay? What happens if we take a molecule and we put it in our sample and we say it rotates in the positive direction? And then we find the mirror image of that molecule. Where should it rotate light? In the negative direction. An equal magnitude as the positive. So if we take a mixture that's 50-50, what happens to our optical rotation? It doesn't rotate. Our light comes in, sees one of those, rotates to the right. It sees the other one, and it rotates equal and opposite back to 0. The net result is we see no rotation in our sample.
And it shouldn't matter the direction we hit the molecule from, right?
It does not matter the direction we hit the molecule from. Okay? This is where we end up with our dextrorotatory and levorotatory. You will sometimes see reference, and this was done unintentionally. Those should not be capitals. You might see reference as a lowercase l and a lowercase d. They're typically written in italics. Okay? Not capital L, not capital D. An entirely different system. Okay? Which I know is obnoxious, but that's blame the biochemists. Make it worse, blame the biologists. Okay? So, not the same as RNS, because RNS applies to atoms. Optical activity applies to the molecule. Okay? Actually, before we do that, let's go through, and so now what I want to do is, again, just come up with some numbers here. These numbers are not specific. Okay? Let's say we take the R enantiomer, we run an experiment with X concentration, and we get negative 110. 110 is too far. Negative 33 degrees. If I take that exact same concentration, but of the S enantiomer, the answer I get is positive 33 degrees. Equal but opposite. Okay? Just like R and S. They are opposites of each other, so we'll get the opposite magnitudes here. The thing that's kind of neat about optical activity is we can quantify it. We already talked about the things that are important in that quantification. We've got concentration and path length. Okay? So when we go through and report, say, a positive and a negative for those two, I don't even remember if this is what I said.
Opposite.
Yeah, it's not going to matter, right? Remember, it's arbitrary. Okay. Those values are from the experiment. I need a way to normalize that data. Think back to your experiments. If you went through and completed an experiment and obtained 5 grams of product and I obtained 20 grams of product, who did it better? We have no way to conceive of who did it better until we understand something about how much each of us was supposed to make. You were supposed to make 6 grams and you made 5. That's pretty solid. I made 20 and I was supposed to make 10. Okay? So either I deserve a Nobel Prize or I really screwed something up. Okay? So we have to normalize our results. That's what's happening when we refer to our rotations. So in most cases, what you are looking at is not the observed rotation from the experiment. You're referring to the specific rotation. The specific rotation takes into consideration the observed rotation, the concentration of your sample, and the path length of the sample holder. We also run into some weird things when it comes to units. Your observed rotation is just read out of the polarimeter, so not a big deal. Polarimeters are what read all this, in case you missed that. C is our concentration in units of grams of compound per milliliter of solvent. What unit system is that? I have no idea. I mean, it's not density, because density is grams per milliliter of the same compound. Compound versus solvent. Okay? So it doesn't really match any kind of unit system. The reason why we use this, old technology, it was how they were able to measure and build their individual experiment. Why did we not switch over to a more appropriate unit system that we would use in common occurrences? Because they decided to not change. Okay? And by insisting in their old ways, they prevent us from then changing in the future. Okay? So that's the only reason we use that system. The path length is always specified in decimeters. Okay? Again, why? You plug all these numbers into your calculations, it comes out spitting out with an observed rotation that gives you a number that somewhat makes sense, okay, or that looks reasonable. Okay? So these are kind of arbitrary units fit to match the experiment designed. Okay? What can we do with this? Okay? Well, there's lots of things we could do with this. there's lots of calculations, which I think I have on that next slide. So let's skip that for the moment and think about the more appropriate thing to do for a multiple choice test. Because I will not ask about calculating concentrations or calculating optical activities, because it's not worth the time spent in dealing with the mathematics. What I do want you to do is understand the theory. Okay? So, which of the following will show optical activity? The R enantiomer of a compound. Yes, that should show optical activity. So we'll call that a yes. Is it plus or minus? Okay. We have no way of knowing until we run the experiment. Okay? So we cannot determine plus or minus just based on the information that it's an R enantiomer. What if it is a meso compound? Okay, what did a meso compound mean? We have two chiral atoms that are mirror images of each other. We have an internal mirror plane, which then means really what we're saying is we have a compound that is half R and half S. So light comes in, hits the R, and it rotates one direction, comes in, hits the S, and rotates back and cancels it out. So optical activity? No. A mixture of enantiomers. Okay, 1 to 3. 1 part S, 3 parts R. Should we have optical activity? Yes. The excess of R is going to cause it to have the optical activity of the R sample. Another mixture of enantiomers. Well, the first one was a mixture, so why not this one? This one, 1 to 1. No. Said another way, it's 50%. Not meso, because this is saying a mixture of enantiomers. By having enantiomers, they are by definition two structures. Okay, so it's not meso. It's kind of qualitatively similar to a meso compound. Last one, a mixture that has a 0% enantiomeric excess. What did 0% enantiomeric excess mean? Okay. Our enantiomeric excess was the one in greater concentration, let's say R minus S. For that to equal 0, what does that mean? They're the same quantities of R and S, which then means no optical activity. Okay? It's the last kind of tricky curveball that we get thrown in there. Questions about those? Okay. So the last part I kind of want to skip through a little bit. This is going back to our enantiomeric excess, shown as capital E. This is the percent of our higher enantiomer minus the percent of our lower enantiomer. Okay? So depending on our or whatever our solution is, we may end up saying the R is an excess or the S is an excess. Okay? It can also be determined by looking at the optical rotation. Okay? So our enantiomeric excess can be calculated by looking at the specific rotation for your mixture and then dividing by the specific rotation for the pure enantiomer. Okay? Multiply by 100 and you now have your enantiomeric excess. Okay? This can be used to then back calculate the relative concentrations of both your R and your S compounds by just running an optical activity experiment. So how many people are excited about doing a calculation? Anybody actually want me to show the calculation knowing full well that you won't ever see this on a test? Okay. If anybody is interested outside of class, feel free to talk to me. It may pop up actually in the lab. In fact, I know it will pop up in the lab. Yes, I think it will pop up in the lab. We'll talk about it then. Okay? Everybody okay with that? Okay. Last part about our optical activity. This comes from our RS nomenclature, which I posted online. As videos go, it was only 30 minutes, so not that bad. Okay. The last 10 minutes of which went over this topic. Since I'm fully aware that most of you, or at least a good half of you, probably aren't going to bother to watch the video, figured we should at least talk about Fischer projections because it's a common thing that pops up. Fischer projections are just another way of looking at a molecule. Like Newman projections, like line angle, like our wedge dash, all of that. Right? The only reason we really use Fischer projections is because of biochem. When you move into biochem, we get molecules like the one shown here. Okay? That one has how many chiral atoms? 4 chiral atoms. So we could go through and assign R's and S's to each of those and identify all those relationships. It gets nasty and it gets messy. Okay? So Fischer came along and said, this is too much work. I want to simplify it. So he decided to change his viewpoint on the molecule to better or quicker, more easily see the relationships between those chiral atoms. So if we take a look at our model, theoretically I put this together correctly. We got come on. Rotate. Good, put it together. So there's our model. Everybody see it? So what we're going to do is change our viewpoint on the model such that our carbon chain is still vertical, but I want to change it so that my substituents are kind of aimed at me. So I'm going to look at this kind of on end. So I'm going to turn it here. Right? And you may look at that, well, that doesn't really clarify anything, and I'd agree with you, it doesn't. Okay? But what I attempted to do with this is show that change. So now what we're going through and doing is trying to look at that shape all the way down. So we start at that first carbon. The carbon chain is going away from that first carbon. Everybody see that? The OH is located on the right, the hydrogen is located on the left. So all I've done is just kind of turn the molecule. If we look at the next carbon, this is where things are going to get weird because we've already started to specify bonds as dashed. That next carbon, okay, where is the carbon chain going from it? It's going towards you, hence I'm showing the wedge. Where's the OH and the H? Both going away. Okay. Anybody look at that and go, oh yeah, that's obvious. Okay. A couple people can at least see it. Still not an easy way to look at a structure. So Fischer wanted to do the next manipulation. He wants to make sure that everything is located relatively in the same plane. So he decided to define the carbon chain as always going away from whatever carbon you look at, every single one. So that first carbon, it's already in that proper orientation because the carbon chain is going away from it. You look at the next carbon though, so change your view on the molecule. The carbon chain is not going away from that center carbon. So what do you have to do? You have to rotate it. Now when we look at that second carbon, what happens? Carbon chain. Carbon chain is going away from that carbon. Okay? So he's done the rotation. Okay? And we then move to the next one. And you'll notice, well, now that one's all goofed up, so we do a rotation there. Yeah? Okay? We move to the next one. Is that carbon chain? No. So we need to adjust that so it's now away. And you notice that as we go through and do this, all he's trying to do is simplify the drawing out so that when we start at our top carbon, OH is on the, what is that, left? That's your right. You're right? Right. You're right. We look at the next carbon. The OH is on the left. We look at the next carbon. On the right. Look at the next carbon. On the right. Okay? Should we look at the next carbon? Why not? It's not chiral. The only reason we're orienting this is to get a better viewpoint on our chiral atoms. That's it. Okay? The next part that everybody seems to be confused by is, well, I mean, among other things, is getting it into this orientation is just kind of bizarre, and how does that actually work out? And so what I attempted to do with the video is then show what the result would be if we then take that model and take it back to the side view. And what happened to our model? It coils back on itself. Why did we not draw things like this to begin with?
Because it won't exist like that in nature.
Not everything is a chiral.
Not everything is chiral, so that could be helpful. Okay. The other big reason, take a look at this Newman projection. What type of Newman projection have I got shown there?
Eclipsed.
It's an eclipsed Newman projection. To draw the Fischer diagram, you have taken every single one of those carbons and you have eclipsed every single one of the bonds. Is that a stable conformation?
No.
No. So we don't typically show them in a Fischer projection or Fischer orientation because we're trying to draw the highest energy structure. Okay? When we tend to draw organic molecules, we draw the lowest energy. Okay? So why would Fischer bother to go through all of this trouble? Okay? Well, this comes from looking at R and S and some other things. This lovely black box is because my computer, for some reason, has decided that anything I draw and own and insert into the projection decides to turn into a black box so nobody can see it. This image is the previous image from the last slide. It's this guy right here. Okay, one and the same thing. Once we've converted it over to that, because we've defined everything, we now don't need to specify wedges and dashes because it's defined to be in the Fischer projection, which means I can simplify the structure down to this model. Okay. What's even more fun on this is this image here is copied and pasted from the internet. I don't own this one, and yet I'm allowed to show this one. Freaking irritating. Okay. Why is this so much better than looking at line angles? It isn't really. Okay, it's just a different perspective. Okay. Why did Fischer go through to draw these? Well, a couple things comes out of it. When you look at carbohydrates, you can look at them as straight lines. You can also look at them as, most carbohydrates do what? Form rings. Look up the structure of glucose, fructose, sucrose. You'll very typically find them in ring structures. Why? That could be why Fischer tried to draw things out as rings. Right? So, the next part of this, assigning R and S, because you could be given a Fischer projection and said, define the chiral atoms, or the R and S system on every single one of the chiral atoms. So you've got a lot of chiral atoms to go through and identify. Those of you that watch the video or know your nomenclature rules for R and S, what do we have to do? We have to rank priorities for every single one of those. So let's start at the top. We want to look at the priorities for the 4 groups attached. Oxygen takes highest priority because it has the largest atomic mass. Okay? But there's an oxygen up here. It's connected to a carbon. So I'm comparing carbon to oxygen to carbon to hydrogen. Okay? Oxygen will have the number 1 priority. So which one do we want to look at next? I'm always surprised by this, why everybody wants to go kind of sequentially. Hydrogen. It's the lowest we can get. Assign that. And it's now easier. Okay, now you're at a 50-50 between those two. Okay, which one becomes 2, top or bottom? Okay. First thing to remember, where did we put our highest priority atom in our carbon chain in a Fischer projection? At the top. Guess which one's the highest priority? The top. Why is the top higher priority than the bottom? So we go out to carbon versus carbon, no difference. We can then go out to hydrogen, hydrogen, no difference. We go out to oxygen and oxygen, no difference. Well, the bottom one goes down to a carbon. What does the top one go out to? The structure is drawn correctly. You got to watch out for abbreviations. How many bonds are currently shown to that carbon? 3. It means it's missing a bond. A lot of people tend to jump with implied hydrogens. I can't imply hydrogens, I've already specified it. It's a double bond to the oxygen. There are technically 2 bonds to oxygen on the top carbon. There's only 1 bond to oxygen in the bottom carbon. That's why the top one gets higher priority. Our next step in determining RNS, okay, so good. We heard 2 answers, and those are the 2 answers I wanted to hear. First answer I heard was start to connect 1 to 2 to 3. Okay, and we could look at which direction we're turning. Which direction are we turning? We'd be going counterclockwise. Counterclockwise means S. And we'd be wrong. And we'd be wrong because before you do your circles, you have to ensure you're looking at the molecule properly. The proper way to assign RNS, lowest priority must be away from you. In a Fischer projection, the groups on the side are defined as towards you. You are looking at the molecule from the wrong direction. Okay? So we could go through and spin, flip, and rotate the structure to get it in the appropriate conformation, or we have an easy answer with our hydrogen. Which way is my hand turning? I have to close my eyes to do this. Really, which way is my hand turning? Okay? Just by changing the direction at which we look at the molecule, we switch it. Okay? This is a 1-for-1 switch because we're looking at it from the wrong way. So if we say that this is rotating to the S or counterclockwise, our actual assignment is R because we've looked at it the wrong way. And we've now done our RS nomenclature system. Where does Fischer come in handy? The highest priority group was located on which side of the molecule? The right-hand side, which begins with R. Okay? Fischer can make R and S assignment a lot easier because of how they set it up. The issue is you have to remember the rules for assigning R and S within Fischer are different from their standard rule set, okay, or at least the shortcut to it. Okay? Last thing I want to address, we talked about plus minus, which applies to molecules. S and R applies to atoms. The last thing that comes up with biochem, particularly Fischer projections, is this idea of capital D and capital L, which applies to the last carbon or the last chiral atom in a Fischer projection. Where is our highest priority group? On the right, that means it is capital D. The whole molecule is capital D. Why? I don't know. That's how they work it. Okay? You'll hear some of the rules on behind that reasoning when you move into biochem if you have to. If you don't have to move into biochem, you can completely ignore this capital D, capital L thing because it won't show up again. Okay? Why do we deal with Fischer? This is half of the family tree of our carbohydrates. Okay? And I don't even think this is the full one. 1, 2, 3, 4, 5, 6. Actually, it's pretty close. Okay? When you move into biochem, you're responsible for knowing the relationship between every single one of those pairs. You're also responsible for knowing the names for each of those. How would you go through and name them? Well, our standard nomenclature for organic would be assigning R and S, same name for all of those. Biochemists don't like that, so they invent gluco. They invent galacto. They invent urethro. What do those apply to? A particular pattern within each of this family tree. Okay, yippee. Okay? So if you thought our nomenclature was bad, get really ready and excited for biochem. Okay? Questions about any of that? Okay. So, 15 and 16. You guys have already been working, and at least based on some of these, you at least know where to find information. Some of the interpretation may be missing. But you've got the kind of structural information or the basics you need for the exam, which happens to be Wednesday. Not this Wednesday, next Wednesday. Okay. What we will be doing, the only thing that is really new is this first one, UV spectroscopy, we'll talk about the basics of that today, and in theory probably even get into IR. The IR, mass spec, and NMR, what we'll be reserving for class are kind of the nitty-gritty details. The actual solving part of it, you've already seen in those online videos I've put out there. Okay? So hopefully you've watched those and you've been practicing trying to go through and solve. All of that homework, which is a good point, is now posted. Okay? 15 and 16 I have made due, was it next Monday? The nomenclature for nomenclature 2 and nomenclature 3, so alkenes and RNS. Because I posted those late, I've put those due dates into spring break. You will still see nomenclature questions on the exams, okay, but I didn't want to double down on the homework so late. Make sense? Okay. So, UV, what we're doing is electronic transitions to determine something about our bonding patterns. So ultraviolet light is enough to cause electrons to jump energy levels. Okay? So we just record what energy did it jump. Okay? That gives us some information about the orbitals, which gives us information about the structure. IR, we use infrared light. Okay? Ultraviolet causes electrons to move. What does IR do? Which is higher in energy? Let's try that first. UV is higher in energy. UV causes something with no mass to move. IR, lower in energy, is going to do what? Not really a fat load of anything, except cause things to wiggle. Okay? That wiggling we can detect as spectroscopy, and we get different signals. The things that will wiggle, bonds. That's all we're looking at. How do we define a bond? Sharing of electrons between two atoms. That definition, as simple as it is, needs to be memorized when it comes to IR. That's all IR shows you. Do you have a bond between two atoms? Yes? Here's a signal. No? No signal. Simple as that. Ish. Okay. Mass spectrometry. This is a fun one. Literally, okay, you've heard, CSI, all those fun people that go out and do crime scenes, look at blood spatter analysis, all that Dexter stuff. That's what mass spec is, okay? Except on molecules, okay? You are both the assassin and the person analyzing the results afterward, okay? You go in, blow apart the molecule, and then you look at all the pretty pieces. That's mass spec, okay? Not officially part of the curriculum, so it will get greatly simplified. Lots of information is there. We're looking at it bare minimums. NMR, lots of information is in NMR. You are responsible for it. Some of it can get really, really, really daunting. Don't look at those parts. Look at the simple stuff first. Okay? In all of these cases, go to the simplest aspect first. If you have to make it more difficult, then work it and make it more difficult. Okay? All of them are ultimately trying to give us information about our structure. Yeah? I haven't decided quite how to pull that yet. Less than 10%. Let's put it that way. Less than 10% of the exam will be on mass spec. I'll probably put it at 5%. Because it is on the final, I believe. So, our electromagnetic spectrum, this is just to get you an idea of what's happening here. All of these are using parts of the electromagnetic spectrum. Each of those parts have certain characteristic things. Right? Your UV and visible range of energies cause electronic transitions. Our electronic transitions were used by UV spectroscopy. Okay? Molecular vibrations happen when we use IR light. So when we use IR light to study molecular when we use infrared energy to study molecular vibrations, we are looking at IR spectroscopy. Okay? When we move into the microwave and radio, that's when we start to see all sorts of weird things, rotational and nuclear transitions. Our radio frequencies can cause nuclei to change their spin states. Okay? Which may sound kind of crazy. We're messing with nuclei. Oh, that's dangerous. No, it's not that bad. Okay? That's why you're still alive, if you consider it that way. Think about all the radio waves you've seen or felt. Okay? So in each case, you can go back and quantify wavelength, you can quantify frequency, you can quantify the energies. Okay? Depending on which form of spectroscopy, we'll be looking at some aspect of those or of that relationship, but usually in a very minimal extent. So here's our first UV-Vis spectra. Okay? If we take a look, you'll notice that it reports according to wavelengths. Okay? And if we look from 400 to about 700 happens to be the visible range, okay, of our electromagnetic spectrum. This 200 to 400 tends to be our ultraviolet section. Okay? And that's where a lot of our UV-Vis spectroscopy shows up. Okay? Our compounds will absorb energy if they happen to have an electronic excitation that will allow them to do these transitions. That energy gap happens to be matched in pi bonds. And jumping from our highest occupied molecular orbital of our pi bond to the lowest unoccupied molecular orbital. Just like the atomic line spectrum. Okay? Those transitions are what we end up detecting. So for this particular compound, it absorbs energy equivalent to a wavelength at 224 nanometers. So we see a peak there. Where else does it absorb? It doesn't. That's it. Okay? So that's it. There's a peak. That corresponds to the energy gap in this molecule. Can we tie it directly to this molecule? Unfortunately not. But that's not what we use it for. Okay? So, you remember atomic line spectrum? You get electrons jumping between your energy levels. Same thing's happening here, except they're jumping between our molecules. Okay? Which electrons are most likely to excite? These really low energy ones or these higher energy ones? Okay? For the low energy ones, to excite them, what do we have to do? Provide enough energy to go from here to all the way up. How much energy is that? That's a lot of energy. Is that going to be particularly easy to supply? No. No. Our most common transitions are the ones happening from our highest energy electrons and happening to our lowest occupied orbitals, unoccupied orbitals. Hence our terms of HOMO and LUMO. HOMO standing for highest occupied molecular orbital, and our LUMO being lowest unoccupied molecular orbital. When we're looking at our UV-Vis spectroscopy, all we're saying is which of those transitions corresponded to a wavelength or an energy within our spectrometer. That's it. Okay? So how can we use that to determine structure? We don't. Okay? What we use it for is to determine how our structure has changed. Okay? So let's take a look at some... Shoot, I actually wanted to do the orbital diagrams. I forgot about that. So let's take a look at the most likely orbital diagrams for 1,3-butadiene to be evaluated. What types of bonds do we have in 1,3-butadiene? We have sigma and pi. Which of those should we be looking at, the sigma or the pi? Why the pi? They're the highest energy electrons. So when I look at the molecular orbital diagram for 1,3-butadiene, I want to be looking at how the pi bonds interact with each other. Well, how do I make pi bonds? How do I make any bond? Share electrons between two atoms. Okay. Where are the electrons on those atoms going to be located? We can get more specific than that. They're located in our p orbitals. So if I want to look at the molecular orbital diagram for 1,3-butadiene, I want to look at, and particularly for UV-Vis, I want to look at the p orbitals and how those p orbitals can interact with each other. So what does a p orbital look like? Dumbbell. So there's the first one. Where's the next one? Interesting. Different axis. This is the p orbital. The first one's the p orbital for that first carbon. What's the next one? The p orbital for the next carbon. I don't care about all the p orbitals on one carbon. I only care about the ones that are making the bonds. And that next one had better be in the exact same plane. Otherwise, there's no bond. Okay? So it has to be aligned. Where's the next one? On the next carbon, which should be? And the last one? Okay. I'm trying to depict how these orbitals interact with each other. To do that, I have to look at the shading of these. So let's shade that first one. I'm going to look at my lowest energy orbital. What should I do on the shading for the next one? Why should it be the same? So that they can share electrons. Okay. What about the next one? Okay. What happens if I shade the bottom lobe? I can shade the bottom of the other one. Okay. What's happening right through the middle there? There's a node. What happens when you have more nodes? There's no electrons, and it's higher in energy. We wanted to find the lowest energy. Is there a lower energy one than this node? What's that lower energy one look like? All the same phase. What happens if we go up in energy? We now need a node. So our new orbital would look like, we're still looking at p orbitals. We need what we just had, one node. What's the next one? We need two nodes. How can I get two nodes?
They're opposite, top, bottom, top, bottom.
So top, bottom, top, bottom. How many nodes? That's three nodes. Not a bad guess. Didn't work. Try again. Okay, say that again. I'm going to pretend this is what you said because I'm not sure. Still not? Okay.
Trying to make her laugh.
Node, node, and our last one. Okay. How many more should there be? No others because there's 4 atomic orbitals, meaning 4 molecular orbitals. Cannot create or destroy matter. Let's put electrons into these. So now let's draw some lines. There's 1 orbital, 2nd, 3rd, 4th orbital. Ignore the gaps between those being oddly shaped. How many electrons should be going into this molecular orbital picture? We're looking at what orbitals to make, or what bonds? The pi bond. Where's the pi bond? Pi bond can't be on a carbon because a bond by definition is 2 atoms. So you tell me carbon, that doesn't work. Between the carbon and carbon, I see 2 lines between the carbon and carbon. Are both of those a pi bond? No. So, where is it? One of those. We have a line. What does a line represent? 2 electrons. Is there another pi bond? What does that line represent? How many pi electrons need to go into our image? 4. So let's draw those electrons in. 1, 2, 3, 4. Why not put 1 at each level? How do electrons work? Lowest energy first before moving up in energy. So we'll always fill 2 per orbital. We now have our molecular orbital diagram for 1,3-butadiene. What's happening when we hit this with UV light? We're taking an electron from very commonly our highest occupied molecular orbital, which is our highest occupied, a second one, and we're putting it in the lowest unoccupied molecular orbital. And our picture becomes curveball. What happens when that electron comes back down to its initial state? It has to release that energy. If we're lucky, it would release that energy as light, and we would have the phenomenon known as fluorescence. Nifty. Okay. What if it didn't release it as light? It released it as something else. We don't see anything exciting. It's just boring. Okay. Yeah, sorry, that's about it. Okay. So the gap between those is really what we're observing when we're looking at our optical activity. Or sorry, I got distracted by the computer screen. As our UV-vis spectroscopy. What happens if we had more pi orbitals? Right, let's say we move to a system with 6 pi orbitals. What are we going to get? We'll get 6. 1, 2, 3, 4, 5, 6. What's special about this new system? With our 6 pi electrons, we'll jump from our HOMO to our LUMO, and what ends up happening to that gap? It gets smaller. Which means what happens to the wavelength of light? It gets longer, because I'm getting a smaller difference in energy, which means I get a signal in my UV-vis further to the right. Okay? So I can use UV-vis spectroscopy to monitor how double bonds change in a reaction. That's it. If a double bond appears, what would I expect to happen? I should see a spectral shift. Okay? If a double bond disappears, what should happen? It should shift and it should move left towards smaller wavelengths or higher energies. That's it.
Are there any spectroscopies that react without alpha?
IR.
I meant like luminescence. Are there any luminescence that?
Are there luminescent molecules that avoid using pi systems? Yes. Yeah. So we could look at a fancier picture that your textbook goes through and gives you. You'll notice that in their drawings, they don't have the nice orbitals that I had set up, because what they've shown is the average. When you add all those orbitals together, what happens? Your top shaded lobes all overlap, so just show them as one lobe. As we moved up to the next one, what happened? We had the first 2 shaded, the last 2 unshaded, or bottom shaded, which then meant our pi system changes. So it's showing the exact same representation, except trying to draw anything that's up on the screen right now is virtually impossible. So typically you just show the individual orbitals. Okay? Questions about that? So how can we ensure that we're correct on this lambda max, our absorption value? Let's take a look at what happens when we go from hex 1-ene to pent 1,4-diene. We have 1 double bond, and we now have 2 double bonds. What happened to the wavelength? Went up. Oh, I didn't go up very much. Oh, that's a bit weird. I at least was right? It at least went up. Okay. What happens if we looked at trans pent 1,3-diene? Went up a lot. Ooh. What happened?
Location.
What did the location of the double bond do? In our trans structure, so we color in over the top here, the electrons in that pi system are resonance stabilized, which we can refer to as conjugated. If we look at the pent 1,4-diene, what happens if I try and move the double bond? I can't do it because it exceeds the octet at that position. Those 2 double bonds are acting like individual double bonds. Well, what does an individual double bond have for a wavelength? 177. What happens if I add a second individual double bond? Should expect the exact same thing. What happens if those two double bonds interact with each other? Then it's going to go up significantly. Why? What happens to the energy of the double bond as we increase resonance? What happens to the energy of a double bond when we have resonance?
Decreases.
It decreases. What would happen to a wavelength at low energy? It increases. And there's our patterning. Okay. That's it. That's UV vis. The rest of the numbers, you could make other comparisons if you want. Not a big deal. You don't need to stress about. As we have more conjugated double bonds, we increase our wavelength because our energy decreases. Okay? The more conjugation, the higher the wavelength. That's it. Okay? We take a look at a really big conjugated system, beta carotene. What's kind of interesting about that one? We've conjugated those double bonds so much that what light is it absorbing? Visible light, which means when we look at the compound beta carotene, we see color. We see the yellow-orange. Why? Because it's absorbing all of the blue light. Okay? So the colors of our compounds have to do with conjugation. The more conjugation, the more color we can pick up out of them because they start to absorb some of that ultraviolet or that violet light. Okay? So they've got a better picture here. We've got our HOMO-LUMO gap for just an ethene. We only have one pi bond, which means we have only two molecular orbitals. We'd have our HOMO and our LUMO. The gap there is relatively huge. If we jump over to our, what is that, hexatriene, what happens? We're now going to have 6 molecular orbitals. We're going to have a lot more electrons. The gap now between the HOMO and LUMO, much, much smaller. Much less energy for that transition, which then means a longer wavelength. That's it. Questions about that? Okay, that's it. That was literally it for UV vis.
What kind of question would you be asking?
I was hoping I had that in here. I don't. There's some actually good questions and smart work on it. I'm sure you'd love to hear. Let's look at a particular type of reaction. Let's look at this reaction. So the delta means heat. If I take cyclohexanol, right, everybody can get that one? And I add a strong acid and a little bit of heat, what happens? I lose the alcohol and I form water. Okay. The name for this reaction is known as, for those of you that have already taken OChem, nobody? Nobody wants to jump out on that limb? Okay, that's fine. In elimination, we have eliminated a second molecule or eliminated a small molecule from our overall structure. The result of an elimination reaction is water. Well, not necessarily water, it's a small molecule. More importantly, we don't care about the water because there's no carbon. Care about our other structure because it's got carbon. What do we see in the carbon structure? We see the double bond formation. So how would we use UV vis spectroscopy to help us out here? Do we have a UV visible compound? Sorry, a UV visible compound? No, there's no pi bond. So if we ran the UV vis spectrometer on our starting material, what would we see? Nothing. We run the reaction, what do we see? We see a peak because we have a pi bond. So we can use UV vis to confirm that a reaction occurred because we can now see a peak show up. Simple as that.
So the H plus comes in, but don't you also bump an H off of the ring?
Don't stress on that. This is a catalyst.
Okay.
So if you want to get really, really jumpy on me. Okay. What if we ran a different reaction? Let's say we started with this compound. And we ended with what do we expect to see here? How would UV-Vis help us?
Be less because you lost a pi bond.
We lost a pi bond, which means what happens to our UV-Vis? It's going to go to higher energy, which would be lower wavelength. So we just see our signal shift to the left. That's it. UV-Vis. Done. Okay? Other questions? Okay. IR, kind of our big things on this. Again, we're dealing with all these energies and frequencies and all this other nasty stuff. Our typical range when we're looking at IR runs from about 4,000 inverse centimeters to 400 inverse centimeters. Inverse centimeters is a weird unit. What is the unit on wavelength? Wavelength. It's a distance, it's like centimeters. What's the difference unit on frequency? Hertz, per time. Is this frequency? No. Is it wavelength? No. What is it? 1 over our wavelength, which we define as wave numbers. Why? I have no idea. But that's what we do. Okay? So we're looking at the range of 4,000 wave numbers to 400 wave numbers. And that just happens to correspond to the energy for our individual sample. Okay? And allows us to predict some information about our compounds. When we're looking at IR, it is all about bond vibrations. And a bond was defined as sharing of electrons between two atoms. Which means when you go through and analyze an IR spectrum, you need to be defining two atoms. What happens if you define more than two atoms? You're looking at multiple bonds, which means more than likely what you just labeled was wrong. Okay? So be very, very specific when you go through the label. You're looking at a bond, which means two atoms. There are some types of stretching that can involve multiple bonds. All of that stretching is more complicated. Do you want to look at more complicated things? No. So when you define your IR, atom, do it. Okay? And that comes from our basic vibrational stretches. Okay? If we take two atoms connected to each other, I can pull them away and bring them back in. There is one stretching mode. What's another stretching mode that we could do with those same two atoms? You can bend. Okay? It's still a vibration of that bond. Those are your common bond vibrations. That's what we end up using when we look at IR spectroscopy. Okay? Stretching frequencies, there's some patterns that you can kind of pick up. Not that big of a deal, but you can expect to see a question along these lines. It's something that I will freely admit I have to memorize every time I go into a test to talk about this stuff because I don't bother to remember it. Okay? If we change the atoms, either the mass, or let's change the mass of the atoms, is that going to change the vibration of the bond? Yeah, because the mass is now going to make it more or less difficult to make that bond vibrate. What happens if you change the spring? Is that going to change how the bond vibrates? Yes. So what we're looking at within this table is trying to pick out some kind of common patterns. In this first case, what's happening? We're changing the mass of one of the atoms. As we increase the mass of that atom, what happened to our frequency? It decreased. So we have a trend there. Okay? That's all they're trying to represent there. What happens as we go from a single bond to a triple bond? It's a stronger bond. What happens to our frequency? It increases. Okay, or sorry, our wave number. What happens to correspond to our energy? Wave numbers. Wave numbers and energy are directly related because the wave number is 1 over the wavelength. So the higher that value, stronger the bond. We can use that information to kind of correlate and come up with some estimations off things. The biggest one is this frequency increasing with the increasing bond energy. Okay, and that should really be saying wave numbers. It's not the best thing to be looking at our frequency. Okay. We will end there and pick up again on Wednesday. We will probably be getting into spectroscopy.